Welcome back to class 12. Here are some additional examples out of Cengel. This is example 4.8, heating of a gas in a tank by stirring. I like this problem. We're also using English units here to give us an opportunity to mess around with those. An insulated rigid tank initially contains 1.5 pounds mass of helium at 80 degrees Fahrenheit and 50 psia. A paddle wheel with a power rating of 0.02 horsepower is operated within the tank for 30 minutes. Determine the final temperature and the final pressure of the helium gas. Just an excellent problem. I'm not telegraphing it, but this would be a great problem for an exam, I think, because it's got so much in it. All right, so much just, it seems so simple, but you need to have exercised your brain. So let's see, things they said it was an insulated rigid tank, right? So there's not going to be any work except for the paddle wheel that's coming into the system. We could draw a little boundary right here, and we could identify that we have work coming into the system, right? That'll generally be negative, by the way. We would indicate. Usually work is out, but that's cool. So yeah, we could even write that down. U2 minus U1 is equal to Q1 to 2 minus work 1 to 2. But it's insulated. So, but the work is in. So we're going to take U2 minus U1. It's going to be equal to negative work 1 to 2. Simply because the work is coming in, and this equation is written for work coming out. So we'll say the work, I don't care, it doesn't matter which way we write the equation, I guess. All right, we'll get back to it. So let's get to, they tell us the power and then the time. So that should give us an indication that we want to we can find out how much work energy is being put into this thing. We have a units conversion issue of horsepower. I'm not quite sure if I recall. I think I have said something about the units. Yeah, I did in the first day. Yeah, you want to come into here and find power. Let's see. Let me find power. There's pressure, there's power. All right. And the units of power. We have, here's a horsepower. 1 horsepower is equal to 2,544.43 BTUs per hour. Let's go BTUs because that's what we're used to, or that's what we usually use in US units. So what we could say is this work, here I already started, it's going to be equal to the power, which I'll write like work rate times time. So we'll go 0.02 horsepower, multiply it by the 2,544.43. These are BTUs per hour, BTUs per hour, per horsepower. That's a nice way to write it. And then we also need to multiply it by the time. Yeah, right there, time. So that's at 30 minutes, 0.5 of an hour. We can do that. So we get 25.45 BTUs. Okay. We might need to find, so we're going to look up the constant, the specific heat constant for helium, but we need English units. And not there, here, gotcha. Helium, boom, 0.744. So we want, is it already used? No, wait. In the other book, it's different. They have 0.753. Interesting. How can it be so different? That don't seem right. All right, well, I'm going to write it down. So table F.4 CV of helium is short attention span 0.744, and units BTUs per pound mass degree ranking. BTU per pound mass degree ranking. That's good to know. All right, so we're all kind of set up. We have it like right up under here. Let me, I'll write it down this way. Work is equal to the change in U, which is mass times CV, T2 minus T1. All right, this is the change in U right there. And so we're going to go 25.45 BTUs. It's going to be equal to the mass was 1.5 pounds. This was 0.744 BTU per pound mass degree Rankine. And these, even though they're not Rankine, we can go ahead and, because we're just going to subtract from the two of them, we're going to take T2 minus 80. Boom. And T2. All right, so I think I cheated and I used the numbers without calculating them. That's where that came from. So 25.45 divided by 1.5 divided by 0.744. I think I need to add 80 to that. Yes. So I get 102.81. If I want to put another one in there. Degrees Fahrenheit. The other book got 102.5. No big deal, but that's one of our important things to do. And I think even though this process is undefined, it's kind of a constant volume process. Yeah, it's a constant volume process. Okay, because the volume never changes in there. So what we could go ahead and do is go do ideal gas law and go PV equals RT, or PV over T is equal to PV over T, right? We go 1, 1, 1, 2, 2, 2. But these are, boom, constants. Right, that's equals to that right there. So you could say that P2 is going to be equal to, I'm terrible at this. I can never do this the right way. I wrote it down differently over there, so it always bothers me. I can't stop myself from doing this right here. P1 times T2 over T1. Yes, that's right. Okay. So we start out with 50 psia, but to be able to do this ratio is really, this is where the ideal gas is a trap. It's a trap. Watch out for this trap. Do not write down 102.81 because you can't do that. That ratio is not true. It has to be absolute scale. So that's going to be 102.81 plus 460. I tell you what, you'll fall for the trap. We all fall for the trap. There's going to be 80 plus 460. Don't fall for the trap. P2 is equal to, and this alone is a good reason to show this example. People get lazy. I don't think it's not fair. I wouldn't say it's lazy. It's just won't pay attention. 52.11 psia. Well, not much change. Well, change from 80 degrees here. That's a noticeable change. That's not that much of a change, right? So anyway, I'm good with that. Let's go do another one after this. I don't know how many more I can do. I'm gonna go to bed soon.